This video shows you how to set up a simulation of a micromodel in Comsol version 6.2. We want to set this up using laminar flow physics. So we'll go and include the physics here. It's under fluid flow, single phase flow, laminar flow. Now this model will use some kind of complicated geometry to represent a micromodel. It's a regular geometry, and I'm going to set up the geometry using these global parameters. If I specify parameters as global parameters, then I can use them to define the geometry specifications. And I'll show you how that works. Here's the geometry, and we're going to build this geometry as a series of circles. So the first one is defined here, and you can see the radius is defined using the variable large rad. That's a global parameter that we defined, and that's going to look like this. We go and build it, and then we go and find where it's been plotted. There it is. And we'll zoom out, and we're going to copy this as a 5x4 array with the displacements as I show there. The displacements are defined using those variables. And I'm going to copy that grain and put it there. And now I'm going to copy that grain also as a 5x4 array to fill in some of the space. Now I'm going to put in a circle that is called small rad. This is a smaller grain that goes in between the big ones. And it's copied as an array, and I put in another one and copied it as an array, and I get that. And now I'm going to get rid of the grains that I don't want. Just delete them. And this is my geometry. Those circles are solid grains, and the space between them is the pore space where flow is going to occur. I'm going to assume that we're just going to use water for the flow, so I'll go to the material library, the built-in library, scroll down to the bottom and select water as the fluid, and I'm going to include it in the pore space. The laminar flow also just really needs to be defined in the pore space. I don't need to define laminar flow in the grains. The fluid property, I just selected the water as a fluid property, so I'll use density and viscosity from material. The wall boundary conditions are default, and the inlet boundary condition on the left side is going to be pressure boundary of 1 Pascal. That's a very small pressure. And on the right side, the outlet boundary is also pressure, and it's a pressure of 0. So I'm going to use a boundary layer mesh, and this is a good mesh to use for fluid flow problems because it has a fine mesh right along the boundary of the solid boundary. So if we zoom in and take a look, you can see these rectangular elements that get quite thin right along the boundary. That's to resolve the gradients that occur right at the boundaries or at the wall. So we'll solve this, and here's the result. You can see that this is a plot of the velocity, and you can see some high velocities at the pore throats where the fluid has to go through a very narrow opening. And this is a regular array, so all of those pore throats will have that high velocity. And this is a streamline that's included in the plot, and this shows the paths. Here's the pressure. These contours are essentially straight contours showing a uniform pressure gradient. If we were to zoom out and average it, it would be a uniform gradient.